Alright, so in this video, we're going to be going over sections 1.1 and 1.2 of chapter 1 from the textbook. So this video is just going to go over some definitions and some examples that you can find in the text, and is just meant to help you answer some homework questions and some of the quiz questions that you'll see. So we're going to start off with the definition of a function. So a function is a correspondence between two sets of elements, such that each element in the first set, so in the domain, corresponds to only one element in the second set, which is the range. So if we look at these examples here, these tables, we can see that these are all the elements in our domain, and these are all the elements in our range. And so in order for this to be a function, we want to make sure that each element here corresponds to only one element here. And looking at our table, we can see that this is the case and that this table represents a function. Now, if we're to look at table 2, for example, we see, again, this is the set of our elements in our domain, and these are the elements in our range. And we see that -2 corresponds to this element 4 in our range, but so does +2. Now, this is fine, actually, because in our definition of a function, we just need that every element in our domain corresponds to only one element in our range. So this 4 here is the result of -2 and 2, but that's fine because -2 and 2, their only result is 4. And same with -1 and 1, the only result in our range for -1 is 1, and the only result or output in our range for 1 is also 1. So that's totally fine. And lastly, our output for 0 is 0. Now here's where this might be solidified a little bit, is looking at table 3. So we see that 0 here corresponds to 0, so that's fine. However, this input here, 1, corresponds to 1 and -1 in our range. So automatically this tells us that this is not a function, because remember in our definition it says that each element in the first set corresponds to only one in the second. And as we can see here, this 1 corresponds to 2 elements in our second set or in our range. So this automatically tells us that this is not a function. And same for these elements as well. 4 corresponds to 2 elements in our range, and then 9 corresponds to 2 elements in our range. So table 1 and 2 are functions, and table 3 is not. Now, functions are often specified by equations, and so this follows the same rules as well. In an equation with 2 variables, we want to get exactly one output for each input. If that's the case, then the equation does specify a function. And so for example, if we were given this function here, y is equal to x times x minus 1, and this is our domain here for all values of x greater than or equal to 1. We see that for each input, each x value, we obtain only one output, only one y value. So for example, if we were to input 5 into this equation, we would get 20, and only 20. And if we were to input 1 in this equation, we would get 0 and only 0. Same for the square root of 5. Plugging that into our equation here, we get roughly 2.76. And that's the only output we get. So this is an example of a function that is specified by an equation. All right. So a little trick here to tell if a graph is a function is called the vertical line test. So an equation specifies a function if each vertical line in our coordinate system passes through at most one point on the graph. So for example, we were given this equation here with this graph. What we can do is we can draw a bunch of vertical lines just like this on our graph. And if for every single vertical line it only intersects our graph at one point, this tells us that we do have a function. Now, if we look at this graph here on the right, doing the same thing, drawing a bunch of vertical lines, we see that each line actually passes through our graph at 2 points. So this automatically tells us that since this vertical line is intersecting our graph at 2 points, that we do not have a function. All right, so in our last example here, going back up, we were given the domain of our function. I was specified, but this actually is not always the case. And so what we'll look at is kind of this general rule of thumb for the domain of a function. And that is, if we have a function whose domain is not specified, we'll assume that the domain will be the set of all real numbers except those numbers that do not output real numbers when plugged into our function. And I know that's a bit of a mouthful, but we can kind of just think of it as the domain is going to be the set of all real numbers, but we're going to exclude those numbers that make our function undefined in some sense. So let's illustrate this with an example. Say we're given this function here, this equation here, y equals square root of 4 minus x, and x is our independent variable. And what we want to do is find the domain of this equation. Now, what we're going to do is assume that it's the set of all real numbers, except those numbers that don't output real numbers when plugged into our function. So we need to remember a few things about this equation here. We're given a square root function. Now remember, if we were to take the square root of a negative number, we'll actually get an imaginary number, which is not part of the set of real numbers. So what we need to do is we need this equation here to be a real number. So and in order for this equation to be a real number, the inside needs to be greater than or equal to 0, right? Because if it were less than or equal to 0, or sorry, just strictly less than 0, then we would have a negative value in our square root, and the square root of a negative number is imaginary, which is not a real number. So this is our restriction on our inside of our square root. And what we want to do is solve for x. So if we were to add x on both sides, we get x is less than or equal to 4. So this tells us that the domain of our equation is all values of x that are less than or equal to 4. And then in interval notation, this is going to be negative infinity all the way up to 4. And remember, whenever we have negative infinity or infinity, we're going to use a parenthesis because that's not a number that we can actually get to. And then since we are including 4, we are using a bracket here for our interval notation. All right, so that is the domain of our equation because all of these values will result in y being a real number. All right. In addition, we should be able to look at our function here and evaluate a few values. So what we want to evaluate is f of 6, f of x plus 3, and we also want to find the domain of our function f of x. So just given f of x here, we should be able to do all 3 of these. So the first thing that we're going to do is look at f of x. And so all this means is that we're plugging in 6 into our f of x function, we're plugging in 6 wherever we see an x. So we have 12 divided by 6 minus 2. So we end up with 12 over 4, and that's equal to 3. Okay, so not too bad. Now let's look at f of x plus 3. So we're doing the same exact thing here. All we're going to do is plug in x plus 3 into x wherever we see an x. So we have x plus 3 minus 2 on the bottom. And so this comes out to 12 over x plus 1. Now, something to note here, for f of 6, we get an actual value. We get 3 here. And this is because we're evaluating our function at that value. Whereas for here, when we're looking at f of x plus 3, we're left with another function because we do not have an actual input value for x here. Okay, now the last thing we want to do is find the domain of this function. And remember, our rule of thumb is that the domain is going to be all real numbers except the numbers that, when plugged in for this x here, make this function undefined. So remember, we can never divide by a 0, right? If we were to divide by 0, we get an undefined function. So this tells us that our domain will be all real numbers besides those numbers that will make us divide by a 0 here. And it's pretty clear that that excludes just 2. If we were to plug 2 in here, we would get 12 over 0, which is undefined. So this means our domain is all real numbers except 2. And that's how we would write that. And then in interval notation, we would write it as this. So we're going from negative infinity up to 2, but we have a parenthesis here, so we're not including 2. And then we're going from 2, again not including it, all the way up to positive infinity. So that would be the domain of our function here. And in addition to evaluating functions as specific numbers, we should be able to evaluate them at expressions that involve one or more variables, which is kind of why we wanted to go over this one so we could see what it looks like, because we will be looking at what's called the difference quotient a little later on. And this is shown in more detail with a few examples in the book. I think it's on page 10 if you want to look into that further, but this will come back around. All right, so we'll look at a few applications in this text. And the first one, we'll be looking at this profit loss analysis, which will help us answer questions related to profit and revenue. So our equation here, this P is equal to R minus C. P represents the profit, R is the revenue, and C is the cost. So this is pretty straightforward. If P is less than 0, then we have a loss. If P is equal to 0, then we'll break even. And if P is greater than 0, then we do have a profit. Now, these are the 4 functions that we'll be working with. We have our cost function, our price demand function, our revenue function, and profit function. And so here is a little blurb on the side. We just have these positive constants here that will be determined from the context of the problem when looking at these functions. All right, so we'll look at an example here. So we're told that a manufacturer of a popular digital camera wholesales the camera to retails throughout the United States. Sorry. Using statistical analysis methods, the financial department in the company produced the price demand data in table 4, where P is the wholesale price per camera, and at which X million cameras are sold. And something to note here is that as the price goes down, the number sold goes up. So we have our price demand function here, so our P of X, and looking at that, we see that our M is 94.8 and our N is 5 here. So if as X increases, then this value decreases. So what we want to figure out is the company's revenue for this camera and its domain. So the first thing we can do is recall our revenue function is equal to X times P. So we'll just write that here. And we're given, this should be P of X. And we're given here that P of X is this. So all we have to do is plug that in. And this becomes our revenue function. Now our domain here actually does not change. So we're given that our domain is this here. So x is between 1 and 5, or sorry, 1 and 15, and including those numbers. And so it does not change from our original function because we're just multiplying our original function by this variable x here. And so it's not changing where the function is defined when we do that. Okay, so you should see a few questions like this on your homework as well. Just have these equations here on hand. All right, so switching gears a little bit, we are going to be talking about elementary functions, graphs, and their transformations from section 1.2 of the textbook. So we'll start by looking at these basic elementary functions here. We have x as our identity function, we have our squared function, cube function, square root, cube root, and the absolute value function. So essentially these operations are being performed on x. And you can refer to the book for graphs for each one of these elementary functions as well. And then something I just wanted to include in here is the absolute value function. So it is interpreted as the distance from the origin on a real number line. So here's a real number line here, and as you can see, this is the distance from our origin here. So it's kind of how the absolute value is interpreted. And so we're given this piecewise function here. The absolute value of x is equal to negative x if x is less than 0, and x if x is greater than or equal to 0. All right, so now let's talk about some transformations of functions. So first we'll look at vertical and horizontal shifts. And so if a new function is formed by performing an operation on a given function, then the graph of the new function is called a transformation of the graph of the original function. So for example, these graphs here, f of x plus k and f of x plus h, are all transformations of our original graph, f of x. So how we can look at this and kind of illustrate the difference between vertical and horizontal shifts is through a few examples. So first we'll look at this example A here, and it's asking how are the graphs of the absolute value of x plus 4 and the graph of absolute value of x minus 5 related to the graph of the absolute value of x. So the first thing that we can do here is just graph the absolute value of x. So we should all know that that graph looks like this blue line here. This is the absolute value of x. And then I would graph the absolute value of x plus 4. And we can do this just by doing our order of operations. Let's say we start with x is equal to 0, then our result is y is equal to 4. So if we have 0 here, our output y is equal to 4. And if we do that for each point in this region, we get this graph here for the absolute value of x plus 4. And doing the same thing for this here, just plug in some values. So if we plug in 0, we get y is equal to negative 5. So plugging in 0 for our x value here, we output negative 5 there. And again, doing this over and over, we get this green graph here, which is the graph of the absolute value of x minus 5. So as you can see, this is an example of a vertical shift. So when we have a positive constant here, we're shifting the graph up, and when we have a negative one, we're shifting it down. So now we're going to look at how the graphs of y is equal to the absolute value of x plus 4 and y is equal to the absolute value of x minus 5 related to our graph of the absolute value of x. So what we'll do for this one is the same thing that we did for example A. We will just kind of plug in values and see what is outputted. So this blue graph here is our absolute value of x. And so if we were to plug in, let's say, negative 1 into our y is equal to absolute value of x plus 4, then our output is the absolute value of 3. So if we were to plug in negative 1 here, we get positive 3 here. if we were to plug in -4 for our x value, we would get 0 here. So plugging in -4, our output is 0. And if we were to repeat this, we would eventually get this graph here. Now, doing the same thing for y is equal to the absolute value of x minus 5, let's say we plug in +5. So if we plug in +5 here, then this becomes 0, and so our output is 0 there. And then again, repeating this process, we would end up with this graph here. So these are examples of horizontal shifts. And something to note here that might be a little bit confusing is just that whenever we're adding a constant like this, we're going to be actually moving to the left. And then whenever we're subtracting, we're going to be moving to the right. So just something to note there. The next transformation we're going to look at are reflections, stretches, and shrinks. So we want to see how the graph of y is equal to a times f of x is going to be related to the graph of f of x. So we'll see that this graph here, y is equal to a times f of x, can be obtained from this graph by multiplying each coordinate value by a. So we're multiplying each coordinate value in here by this value a, and then we'll get a vertical stretch of the graph. And this is the case if a is greater than 1. However, if a is in between 0 and 1, so we'll get some decimal values, anything between 0 and 1, then this will be a vertical shrink of the graph. And lastly, if we were to multiply our function y is equal to f of x times -1, this will result in a reflection across the x-axis. All right, so that was a lot, but what we're going to do is, again, look at an example. So we want to see how the graphs of y is equal to 2 times the absolute value of x and 0.5 times the absolute value of x, and see how those graphs are related to the graph of the absolute value of x. So again, we all know that the graph of the absolute value of x looks like this. And so what we're going to look at is the graph of 2 times the absolute value of x. And again, what we can do is plug in numbers for x and then just multiply them by 2 and see what we get out from it. Let's look at a different value other than 0 for this. So if we were to plug in, let's say 5 for our x here, our output would be 5 times 2. So plugging in 5 for our x value, our output would be 10. So that's where we put our point through here. And repeating this, we would end up with this graph here for y is equal to 2 times the absolute value of x. And doing the same thing for 0.5 times the absolute value of x, if we were to plug in 5 for our x value, we're multiplying it by half. So we would end up with about 2.5. So our point goes roughly around there. And then repeating this, we get this green graph here. Okay, so we're just trying to plug in values for x and see how that helps us visualize how the graph is being transformed. So this was a vertical stretch. So we have our absolute value of x and we're kind of stretching it vertically this way for our red graph. And then we are kind of shrinking it vertically, this arrow here, for our green graph. All right. And lastly, we want to see how the graph of y is equal to -2 times the absolute value of x is related to the graph of the absolute value of x. And again, this is our graph of our original function. And what we can do is just plug in values for x and see what happens. So if we were to plug in, if we were to plug in 5 for our value of x, we would get 5 times -2. So our output is -10 here. Same if we were to plug in, let's say, roughly, I think 2 is around here. So if we were to plug in 2, we should get 2 times -2, so we would get roughly -4 here. So what this is doing is this is reflecting our graph over our x-axis as well as stretching it vertically. All right, so here is a little summary of our graph transformations. So we have our vertical translation, so when we're shifting our graph up or down. And then we have our horizontal translation, so when we're shifting our graph to the left or to the right. And then we have our reflection, when we are reflecting our graph over the x-axis with this -1 out in front here. And then we have our piecewise graph here for our vertical stretch and shrinks. Now, something else I wanted to discuss is that we can combine our graph transformations. So we want to discuss and look at the relationship between the graphs of this here and this here. So what I want to do first is look at our equation and figure out what's happening to our original graph, our identity, which is going to be y is equal to the absolute value of x. So the first thing to note here is we have this -1 out in front. So this tells us that we are going to be reflecting about the x-axis. The next thing we have here is this -3. So this tells us that we are going to be shifting our graph three units to the right. And then this +1 here tells us that we're going to be shifting 1 unit up. And so after doing these transformations, we get the following graph here. So for this one, we see that this is our absolute value, and everything that we're doing to this graph is appearing in this red graph here. So the first thing that we did was we reflected it about the y-axis. So kind of just imagine the graph like this. If we were to reflect it about the y-axis. Then what we did was we shifted it 3 units to the right. So that looks something like this. And then the last thing that we did was we shifted it 1 unit up. And then that is our final graph here. Right, so that's what it looks like if we were to combine a bunch of our graph transformations. All right, and then the last thing that we're going to talk about for this video is piecewise defined functions. So we kind of saw it earlier when we looked at the absolute value of a real number, and it was defined as this piecewise function. So the absolute value of x will be equal to -x if x is less than 0, and +x if x is greater than 0. So essentially what we're saying is that this function is defined by different rules for different parts of its domain. And these are the rules here. So if our values are less than 0, then this is our result. So that's kind of like our rules. And so these functions are called piecewise defined functions. And when we're graphing these functions, what we're going to do is essentially graph each rule, so these guys here, over the corresponding portion of the domain. So what we'll look at are these 3 graphs here. So the first one here, we're given this function here, y is equal to x² minus 2. And we can already see that this is just going to be a parabola that's shifted down 2 units. So this is what it originally looked like, and then we shifted it down 2. Now, our domain here is telling us that our function is going to be defined for all values of x less than 0, and it's strictly less than 0, so we're not going to be equal to 0. So 0 is not part of our domain. So this means our function is going to be defined for all of the negative values, the negative x values in this region here. And then we're denoting the fact that 0 is not included in our domain with this open circle here. So that is what this graph looks like. Now looking at graph B, y is equal to 2 minus x squared, we see that this is again a parabola, and then we have this negative out in front of our function. So this tells us that we're reflecting over the x-axis. So our parabola looks like this. And then this positive 2 here tells us that we're shifting it 2 units up. So this is what our graph looks like. However, we are defined on this domain here. So whenever our x values are greater than or equal to 0, so these are all of our positive x values. So our graph is only defined in this region here. And then there's a closed circle here because we are including 0 in that domain. All right. Now this last graph here, we have our piecewise defined function. And we're saying that in this region, when x is less than 0, this is what our graph looks like. So that's this here. And we have an open circle because we're not including 0. And then in this region, when x is positive and including 0, this is what our graph looks like. And we have a closed circle here because we are including 0. So that's essentially what our piecewise defined functions are. They're just functions that are defined on certain intervals. And there are a few examples in the book that can help you practice graphing these piecewise functions if you want to go ahead and take a look at that. But I think that's all we're going to go over in this video. So thank you.